Hi, this is Hunor Challa from University of Utah, working with Amir Arzani. I will be presenting our work on nonlinear dimensionality reduction of unsteady fluid flows. As we know, CFD data is usually very high dimensional. We can have millions of degrees of freedom in space and thousands of time steps. However, this is not necessarily representative of the underlying dynamics, but it's a necessity for our numerical schemes to converge, and actually natural systems tend to live in low-dimensional manifolds. The first step of reduced order modeling is identifying this new set of low-dimensional coordinates. We can use these coordinates to evolve the time dynamics or to extract underlying coherent structures and flow patterns, which will be the main focus of this talk. The most well-known dimensionality reduction method is principal component analysis with proper orthogonal decomposition. It's very well established in multiple branches of science. It's a non-parametric method and it's computationally cheap. It also gives us these interpretable spatial modes, which we can call eigenflows, that we see on the right for a flow over cylinder case. However, PCA is inherently linear, therefore it has limited expressiveness for highly nonlinear data. To overcome this issue with nonlinearity, another family of methods were introduced called manifold learning. On the right side, we see this three-dimensional S-shaped data set. And on the top right, we see the PCA embedding, and we see that PCA cannot really discover the underlying manifold. On the other hand, the bottom two figures show locally linear embedding and isomap, which managed to unfold this manifold into a 2D plane. We used 4 different manifold learning methods: kernel PCA, locally linear embedding, Laplacian eigenmaps. These two are based on preserving local relationships based on nearest neighbors. And finally, isometric mapping. The downside of these methods is that they need hyperparameter tuning, they're slower than PCA, and reconstruction is not always straightforward. Here we use the reconstruction based on the inverse locally linear embedding. The question of how to obtain visual modes also arises in this case. Another family of methods are autoencoders, which are a special type of neural networks where the output is supposed to be the same as the input. Just in the middle, we have this so-called bottleneck layer, whose dimensionality is much smaller. Therefore, it forces the network to learn a meaningful representation of the data. The question of how to obtain visual modes also arises here, and even if we can somehow obtain modes, they will be not ordered and they will not be orthogonal to each other. So we have our CFD data. We take each snapshot and rearrange it into one long column vector. Then we stack these column vectors next to each other to get this big data matrix X, whose dimensionality is n by m, when n is the number of spatial locations and m is the number of snapshots in time. Usually this is a tall skinny matrix. If we reduce the size of the columns, we are essentially doing spatial dimensionality reduction, and that's needed for reduced order modeling. However, this will not give us these visual modes. To obtain visual modes, we have to keep the spatial size fixed and reduce the temporal size of our data, corresponding to reducing the size of the rows. Each row corresponds to velocity values at a fixed spatial location through time. On the top, we see the conventional way of using the snapshots of our flow field as inputs to the autoencoder, leading to spatial reduction. In the middle row, we see a mode decomposing autoencoder introduced by Murata and others, where the main idea is to use 2 separate decoders for the 2 latent vectors to obtain these decomposed fields, which can also reveal coherent patterns in our flow field. However, they are not similar to PCA modes since these are time dependent. On the bottom, we see the temporal reduction case where we use the rows of the data matrix X as inputs, then we get the visual modes directly in the latent space. We had 3 test cases for these methods. First is 2D flow over cylinder at Reynolds number of 100, leading to periodic vortex shedding. Second is a 2D slice of a turbulent channel flow from the Johns Hopkins turbulence database. And third is blood flow inside the brain aneurysm. An aneurysm is a local bulging of the vessel wall. The unsteadiness in this case comes from the pulsatile inlet velocity waveform. For the sake of brevity, I will only talk about the 2D flow over cylinder and the brain aneurysm in this talk. Here we see the relative reconstruction error as a function of the number of modes, which is the size of the latent space. On the left is for spatial reduction, on the right for temporal reduction. For PCA, both spatial and temporal reduction give the same results, as doing PCA on X and X transpose is the same. For spatial reduction, what we can see is that all nonlinear methods have a smaller reconstruction error than PCA. The other interesting thing we can observe is that the error for the nonlinear methods is not decreasing monotonically. Comparing spatial and temporal, we see that spatial obtains an order of magnitude better reconstruction error. So temporal reduction is harder. And in this case, only the autoencoder is achieving clearly better results than PCA. The manifold learning methods have similar reconstruction error to PCA. Temporal reduction gives us these visual modes that we can try to investigate. Here we see 4 representative modes for the flow over cylinder case for the different methods. We see on the right the mode decomposing autoencoder that its decomposed fields are time dependent. The numbers refer to the mode number. Smaller numbers mean more important modes in all cases except the autoencoders where the order is arbitrary. We can see some similar patterns, for example, PCA1, LLE4, KPCA1, LEM3, ISOMAP1, and autoencoder 2 and full all show the same pattern. What's also interesting is that LLE and autoencoder reveal some more nonlinear structures compared to the other methods. Let's see the brain aneurysm results. For spatial reduction, kernel PCA is slightly better than PCA, and the other 3 manifold learning methods have similar reconstruction error. Again, the 2 autoencoders have the smallest error. For temporal reduction, the manifold learning methods have similar error to PCA. What's interesting to point out here that some of the methods like ISOMAP, the error starts to increase after a given number of modes, which is certainly a peculiar feature that is not desirable. Also, in this case, the autoencoder had the lowest error. Since the brain aneurysm is a 3D case, the modes are also 3D. Here we only see a 2D slice. What we can observe in most of the modes is the main incoming jet to the aneurysm that creates this counterclockwise vortex. Then sometimes the core of the vortex is also highlighted in these modes. If we look at the aneurysm modes, we can see that they are not that different from each other, even though the autoencoder achieved the best reconstruction error. This suggests that the reconstruction method itself is more powerful due to the neural network architecture. We have investigated and compared several nonlinear dimensionality reduction methods for unsteady fluid flows. What we've seen for spatial dimensionality reduction is that all of the nonlinear methods provided a smaller reconstruction error than PCA. Overall, autoencoders had the best results and provided the most flexible framework for dimensionality reduction. We've seen these 2 scenarios of data arrangement leading to spatial versus temporal reduction. Spatial reduction is useful for embeddings that can be used for reduced order modeling, while temporal dimensionality reduction gives us these visual modes that we can physically interpret. Unfortunately, several advantageous properties of PCA are not shared by these other methods. These methods need hyperparameter tuning. Reconstruction is not always straightforward. The modes are not orthogonal to each other, and in case of the autoencoder, they are not even ordered. Some ideas for future work is using finite time Lyapunov exponents for finding Lagrangian coherent structures on the modes themselves. However, this gives rise to some questions as it needs vectorial data, and here we only use the velocity magnitude. Other ideas are investigating how to handle noisy and corrupt data using these low-dimensional embeddings. Thank you for the attention. This work will soon be published in Physics of Fluids. If you have any questions, you can see my contact information here.